Dear students, this is Professor Manoranjan Singha, Department of Mathematics, University of North Bengal, India. Welcome to the 10th clip. In the 9th clip, we have seen that locally compact Hausdorff spaces may fail to be normal, though compact Hausdorff spaces are normal. So the next task should be to check if locally compact Hausdorff space is Tikhonov, which is the immediate weaker separation axiom among the separation axioms that we have discussed so far. And actually it is seen that locally compact Hausdorff spaces are Tikhonov. So let's begin today's discussion by proving the result that says that every locally compact Hausdorff space is Tikhonov. Tikhonov means, completely regular as well as T1. T1 is obvious because the space is Hausdorff given, that is T2, so T1. So just it is sufficient to show that the space is completely regular. And just recall that a topological space X is called completely regular if for any point and any closed set not containing that point there exists a continuous map from this X to close to bounded interval 0 1 as a subspace of R, okay, which maps this point to 1 and this set to 0. Okay, if for every point and every closed set not containing this point there exists a continuous map from X to 0 1, so that this point goes to 1 and this set goes to 0 under this continuous map, then the space X is called completely regular. We know? Fine. So we have to show that a locally compact Hausdorff space is completely regular, and since it is T1, so completely regular plus T1, that is Tikhonov. Okay, so case of the proof. So let X be a locally compact Hausdorff space. Okay, so in order to show it is completely regular, we have to take any point from X and any closed set not containing that point. Okay, so and let A be any point in X and C be any closed set in X such that A not in C, that is A in X minus C, complement of C. Okay, now recall the characterization of local compactness of a Hausdorff space that we have discussed in the 8th clip most probably. Okay, so we need that characterization. Okay, which says that actually there we have proved that 4 statements are equivalent. So one of them was this for any neighborhood of any point, okay, there exists a relatively compact open set which contains this point whose closure totally contained in the neighborhood. Okay, so if we use this result, actually we will use that result twice here. First, for this neighborhood C being closed set in X, so complement of C is open set in X containing A, so it is a neighborhood of A. Okay, so now for the neighborhood X minus C of A, there exists a relatively compact open set U, say U, such that this point A belongs to U, and U of course subset of U bar, and U bar totally contained in this neighborhood X minus C. Okay, so here this U is again a neighborhood of the point A. U is open set containing A, so this U is again a neighborhood of A. Okay, so for this neighborhood U, we will again get a relatively compact open set. Okay, so that this kind of relation holds. Okay, again for the neighborhood U of A, there exists a relatively compact open set V, say, such that this A belongs to V subset of V bar, and V bar subset of U. So if we look at this and this, we see that A subset of V bar, subset of U bar, subset of X minus C. Okay, in a single line we can write this. Okay, so let me write this. So U and V, these are relatively compact open sets in X, such that this point A in V subset of V bar subset of U subset of U bar, and U bar in X minus C. Okay, so the picture is this. Okay, so this is the locally compact Hausdorff space. Fine, and say this is the point A, and say this is the closed set C. At first we got a relatively compact open neighborhood U, whose closure okay, this whose closure is totally contained in X minus C. This okay, X minus C means complement of C. C is this. Then we got another open set, relatively compact open set V. whose closure totally contained in this U. Okay, fine. So this is the picture. Now, since U is relatively compact, so U bar is compact. So since U bar is compact and the space X is Hausdorff, so U bar is also Hausdorff because Hausdorff property is hereditary, and Hausdorff, the U bar is compact Hausdorff, so it is normal. So U bar is normal or T4. Okay, so Eurytion's lemma uh, we can invite Eurytion's lemma in U bar, isn't it? Okay, for this, just let me copy this portion U bar, U bar, this portion, and paste here. Okay, just enlarge it and paste roughly this. So this is U bar. Okay, this is U bar. So this U bar, and this is point A, and this is V, say. So V bar is also like this. Okay, now this U bar is normal. This is normal. Okay, so here U bar is, of course, U bar is closure is closed, and V is open, so V complement is also closed. So V complement is this outside this smaller portion, and U bar is this. So their intersection will be this annulus. This annulus will be their intersection. This is V complement intersection this U bar. Okay, fine. So this is actually U bar intersection V complement, U bar intersection V complement, and this is U bar minus V, A intersection B complement, A minus B. Okay, and look at this. This is point A. Consider this singleton set containing the point A. Then this singleton and this annulus are disjoint, and since the space is T4, space is Hausdorff, so it is T1. So every singleton is closed. So this singleton A is closed, and this annulus U bar is closed, V is open, V complement closed. So this is finite intersection of closed set. So this is also closed. Okay. So this annulus and this singleton both are closed sets. Okay. In U bar also, and this U bar is normal. So by Eurytion's lemma, for these two pair of disjoint closed sets, one is this, another is singleton A. Okay, we will get a continuous map, small f, from this U bar to closed interval 0, 1, which will map this annulus to 0 and this singleton set to 1, isn't it? So U bar is normal. Okay, since this singleton A and this U bar minus V, this are disjoint, disjoint closed sets in U bar. Okay, in X also. So this intersection U bar will be these two again. So these are closed in U bar. This, so by Eurytion's theorem or lemma, there exists a continuous map, say small f, from U bar, from this U bar to closed interval 0 1, such that f of this U bar minus v, this is singleton 0, it means all points of U bar minus v are mapped to the point 0, and f of this a is 1, as I said. Okay, this will go to 0 and this point go to, okay, so in order to show x is completely regular, we need to construct a continuous map f from x to 0 1, okay, satisfying some other conditions. But here we got a continuous map from U bar, which is a subset of x, from this U bar to 0 1. So somehow we have to extend it to the whole space x, isn't it? Okay, so now define a map, capital F, from whole space x to 0 1 as this f of this outside U bar, f will map all points to 0, that is f of x equal to 0 for all x in x minus U bar, and inside U bar, okay, inside U bar, this capital F will send every point via this small f, okay, that is this small fx when x in inside U bar. Inside U bar we already got a continuous map small f, so we are taking help of this actually here in defining a mapping from whole space x to 0 1. Okay, fine. Now let's check the continuity of this mapping capital F defined in this way. Okay, so now if we restrict this F within this U bar, it will be like this small f, which is defined in this way, and if we restrict this f in the V complement, V complement. Look at this. The smallest portion is V in the V complement. If we restrict, then what will we get? Look at this. Look at this. Small f maps every point of this annulus u bar minus v. U bar minus v means this annulus. This annulus. So small f maps every point of this annulus to 0. Okay, fine. So if we take a point from this annulus, it is being a point of u bar, so it will be small fx, but within this annulus small fx is 0, so it will be 0. So if we take a point from this annulus, then capital fx will be 0, and if we take a point outside this u bar, then also by definition of this capital F, 0. So actually outside this V, that is in the complement of V, this capital F is 0. Okay, so outside V complement, outside V, that is from the V complement, this capital F is entirely 0. Okay, so it will be 0 function if we restrict this F within V complement, isn't it? Fine. Now this small f is continuous. This 0 mapping, 0 function. This is a constant function, constant map. So this is also continuous. So both are continuous. Now these and these are continuous. And their nature within their common domain, that is intersection of their domain, is very nice. And if x in their common domain, that is u bar intersection v complement, which is nothing but u bar minus v. So if x in this, then this restriction f restricted on u bar small x, this is nothing but this, but within this annulus this small f takes 0. Within this annulus small f takes 0, so this is 0. And x in b complement, so this is entirely 0, so this is 0. So if this is also 0, so they are same, so they agree in their common domain. Fine. Now we know pasting lemma. Okay, so this is a mapping, this is also a mapping, this is a mapping from u bar to closed interval 0, 1. This is a mapping from v complement to closed interval 0, 1. Both have the closed domains, subsets of x, and in their common domain we see that their images are also same. Okay, so we can use pasting lemma. You know pasting lemma? Just briefly I am recalling. Okay, so we know pasting lemma. This is pasting lemma. Pasting lemma, which says that If f is a mapping from A to say y, G is a mapping from B to y. Okay, and A, B both are subsets of a topological space X. Y also topological space. Okay, and if this fx equal to gx, okay, this A, B are closed. Okay, this A, B are closed subset of a particular topological space X, and fx equal to gx for all x in their common domain A intersection B. Okay, then the mapping H from A union B, union of their domain, to the common codomain Y, defined in this way: hx equal to fx if x in the domain of f, that is A, and this is gx if x in B. Okay, and then this map is continuous. Okay, as if two continuous map has been pasted over their common domain, isn't it? So by this specific lemma, considering this as small f, this as small g, okay, so by this f continuous, g continuous, their domains are closed, and in their common domain they are same. So by pasting lemma, there pasting lemma, this map capital F X defined in this way. First of all, let me define this. F restricted on V complement X. Okay, X in V complement. Fine. X in V complement. Now, here you see that V subset of U bar, isn't it? At the beginning, almost. This. So what is this actually? So V subset of U bar. So V complement, this is small, so outside of smaller portion will be bigger. So X minus V means V complement will be bigger than outside of this bigger portion, that is X minus U bar. Okay, so any point drawn from X minus U bar will be also a point of V complement. Okay, and this F restricted on V complement, this is 0. F restricted V complement 0, so this is 0, and we can write when X in V complement. Okay, so we can write when X in this, because if X in this, then also X in V complement. When X in capital X minus U bar. Okay, fine. So fx is this when X in its domain V complement, and fx is if restricted to u bar x, that is fx. Look at this. Fx is this when x in V complement. It is written in this way. And fx equal to this x, that is small fx when x in its domain, that is u bar, and it is nothing but our capital F. You can look this fx is 0. Okay, so by pasting lemma this fx, this capital fx, which is 0 at x minus u bar, and small fx at the points of u bar, so exactly this mapping. Okay, so by pasting lemma this capital F is continuous. This is continuous, isn't it? Fine. So we are getting ultimately a continuous map F, and its domain, what is the domain of it, is continuous. Okay, so by pasting lemma we should write here F, this map F from this domain is u bar union V complement. What is this u bar union V complement? Look at this. U bar means this inside, and V complements means outside this. If we take union, we will get whole x, isn't it? So this is whole x to closed interval 0, 1. Pasting lemma this f, this given by this is continuous. So in this way we are getting a continuous map. This is a continuous map from this x to closed bounded interval 0, 1. This is capital F. And we have taken any point small a and any closed set C. Now we'll see that this continuous map F maps this closed set C to 0, this point to 1. How? It is obvious, because also this capital FA, what is this? The A in A is within V, that is within U bar, okay, and this capital F within U bar is small f, so it will be small fa, and we know small fa, we have done this, small fa is 1. Okay, so this is 1. Fine. This and f of c. What is c? Look at this. This is c. So c is totally contained in the complement of u bar, isn't it? So c totally contained in x minus u bar, and within x minus u bar, where is it? Within x minus u bar, this fx is 0. Okay, so this is singleton 0 because this is set. This, since this c is totally contained in x minus u bar, and for every point of x minus u bar, that is for every point of C, this fx is 0. So we are getting for every point A and every closed set C in X not containing this point, we are getting a continuous map capital F which maps A to 1 and this closed set to 0. So the space X is completely regular. So X is completely regular. Okay. Since X is Hausdorff, it is Tikhonov. It is Tikhonov. Okay. So hence we are done. Okay. So every locally compact Hausdorff space is Tikhonov. Every locally compact Hausdorff space is Tikhonov. Though compact Hausdorff spaces are normal. So I should stop here. Okay. For the time being, of course. So keep watching. We will meet till the next clip also. Okay. So thank you. Keep watching.